So, hello everyone. Uh, do you have any questions, mm, or shall we already start? Mm, mm, So, mm, yeah. Uh, Last time we studied the following problem: the grain function of Laplace operator in a unit disk. I don't remember what is. Mm-hmm. On the some right hand side. Right? Mm-hmm. Uh, no, are you sure? Maybe I made some mistake. I need to check, but I thought that the right hand side was something like one on some interval for some finite time. Mm. Ah. Oh, this might be so. Thank you. And I will check this and fix if there is a mistake. Thank you. Mm. Yeah. Hmm, we wanted to solve a problem. Uh, Poisson of G of hmm, of Z0 equals to delta function of Z minus Z0. As G of Z0 equals to 0 when absolute value of Z is 1. So uh, it should vanish from the boundary. And we could easily find that, so it is, so we can denote it by D, and this is boundary of D. So, so it was easy to find that grain function for a source placed at 0 is simply the logarithm. Mm. Was mm, and, like oh, maybe like this. Uh, and if you want uh, to obtain grain function for arbitrary z0, we can perform some conformal transformation which maps this disk to itself. And so last time I obtained the general form of such a conformal transformation which preserves this disk. And it turned out that there are some matrices in SU11. But here we can just guess the correct formula. So let us write the following expression. So so we want some function which vanishes at the zero. This is first requirement, and second requirement that its absolute value when absolute value of z is 1 should be 1. And if you want to achieve this, so we at the moment we don't know what is the denominator, but let us try to write it like this. So it is z 1 minus z 0 over z. So it's just some trivial writing. But now let us divide this by the following expression. What happens when absolute value of z equals to 1? It means that the inverse is the same as z bar, right? So so let us write the same denominator here. So we want to write such W that first requirement is that W of z0 is 0. Second requirement is that W, that absolute value of W of e to the I phi is 1 for real phi. It's a conformal map from this unit disk to itself, because it preserves boundary such that it maps the 0 to 0. So it's because if you now substitute this into this, so if you now consider a logarithm of like 1 over 2 pi, a logarithm of absolute value of W of z, and then this is that Laplacian of this equals to 0 when z is different from the 0, and when z goes to the 0, so it's a first statement. Second, so is this clear? So a second statement is that a logarithm of this absolute value of W of 0 equals 0 when z is e to the I phi on this unit circle. And the third property is that So it behaves like logarithm of 1 over 2 pi, logarithm of z minus z0, minus some constant. So this constant is logarithm of 1 minus absolute value of z0 squared, maybe like this, when z approaches z0. And since we know that such function solves the Laplace equation with delta function on the right hand side, we can conclude that this function solves the Laplace equation with delta function in the right hand side. So Poisson of this 1 over 2 pi logarithm of w of z solves so it equals to delta function of z minus z0. So is it okay? Okay. So here, yeah. Yeah, thank you. So in this way we obtained a Grand function for this problem in a disk. And there is a kind of physical interpretation of this. Maybe I'm not sure if one should call it physical, but interpretation of the following. So we want to find electric field created by some charge which is placed inside this unit circle, and so we see that this Grand function has a singularity at z equals to z0, and it also has singularity at 1 over z0 bar. And if we draw these points, so it is z0, and there is some so-called inversion of this point. So it is a 1 over z0 bar. So here we have charge 1, and here we have charge minus 1. So it turns out that if we place two such charges, then this surface absolute value of z equals to 1 becomes equipotential. So if so it means that this distribution of charges on the surface such that it gives us a constant potential. So it's like it is a conductor. It can be effectively modeled by placing the opposite charge at some point, which is precisely 1 over z, which is precisely at distance 1 over r. and it is actually the same phenomenon here and in 3 dimensions, and maybe it's I need to think, but probably it should work in arbitrary dimension because Laplace equation has this inversion symmetry. Probably the charge can be different. So here it is just one plus one and minus one. So in 3 dimensions, these charges are different, and probably it should be the same in higher dimensions. So, so there is such interpretation. Are there any questions on this? Okay, so actually, this method of images can be understood better if we use another model for this disk. So, namely, we can perform we can perform conformal transformation from this disk to the upper half plane. So, namely, let us consider the following expression for let me think. Let us consider W, which equals to oh, so we want a map from the upper half plane to this disk. So let us call this variable z. And we want to map it to the unit disk. Absolute value of z is less or equal than 1. So I don't remember the formula for this map, but it is easy to recover this. So again, we want some transformation, like let us call this variable w. We need some formula for w in terms of z, such that absolute value of this w of z is 1 when z is real. So it means that numerator and denominator, so it means basically that numerator and denominator should be conjugated to each other. And so let us consider something like Let us try something like z minus I over z plus I. So we are sure that it actually maps upper half plane to disk because when z equals to I, w equals to 0. So it maps this point to 0. And if we go to this I goes to 0. WFI is 0. There is point 0 here. We see that it maps to to minus 1. So it is W of 0 equals minus 1. And there is also point infinity here. So, and when z equals infinity, it maps to 1. So, like this. So it kind of fold this real line into this unit circle, and that's it. So if you want to study some problems on the upper half plane, then natural condition is that W at infinity behaves like a constant. If you want it to be something related to a problem in this disk. Oh, is it clear? Right. That this map is actually a conformal map from upper half plane to the unit disk. So, so we can oh, so we can also compute the absolute value and the argument of this W. Mm, So absolute value squared. Oh, maybe it's mm, so interesting. something like this. And also, if you want to draw lines of uh, constant mm, hmm, if you want to draw lines of constant uh, imaginary part of Z, then we see that oh, I don't know, um, maybe it's better to draw another picture. So if I try to draw such lines, then when a real part of the goes to infinity, uh, they all tend to one. So these lines are such circles that touch the boundary of of uh, of this unit circle. Like this. And if we draw perpendicular lines that correspond to a constant real part, then they will correspond to something like this. And it is often useful to draw this transformation of coordinate coordinate grid under the conformal transformation because it helps to understand how it works. And by the way, I told probably I told the definition of conformal transformation in two dimensions only, but a general definition is that it is a transformation which preserves angles. But can in principle change a scale. So it means that so so it means that it should multiply metric in probably an arbitrary dimension by some function, uh, probably coordinate dependent. So it's such coordinate transformation that it multiplies a metric by something. And so in two dimensions, there is this infinite number of conformal transformations that are given by holomorphic or probably anti-holomorphic functions. But in arbitrary dimensions, the only options are oh, the only options are uh, uh, just shift a multiplication by some number lambda times x. And last trivial transformation is an inversion. So for d greater than 2. So this two are conformal for trivial reason, but for this one we should check that it actually preserves the metric. And well, of course, we can generate group by this transformation. So we can take combinations of inversion, shift, and inversion again, something like this. It is called special conformal transformation. No, it's for arbitrary dimension, for d-dimensional space. So if we talk about plane, then these transformations are distinguished, of course, because they are transformations that act one-to-one. In a sense, they in the entire complex plane. But in two dimensions, we have some other notable transformations which act between different domains. So they are conformal in every point, but they can change their domain. And in higher dimensions, there is a local restriction, kind of differential restriction in the form of this transformation, which leaves only these possibilities. So, and yes, of course. So, so in general, we should take group generated by them. And it is well, let me think. Probably it is so d plus 1 1, if I remember correctly. Should be it should be in this one. Actually, I forgot. Okay, so so let us come back to this problem. So why I wanted to tell about the upper half plane? This is because in this case it is more clear what is the meaning of such expression. So namely, let us so it is also denoted by H, not to be confused with quaternions. So we want to solve a problem Laplacian of g of z0 equals to a delta function. With the boundary condition g of z0 equals to 0 when a real part of z is imaginary part of z is 0. Maybe z is on the real line. So physically, it is a problem about the electric field created by some a unit charge at point z0 placed above the metal plane, such that potential of this plane is fixed and equal to 0. So in this case, it is more or less obvious how to solve this problem. We can add, so it is a charge +1, and here we can add charge -1 at point 0 bar. So we can call it image charge. And if we try to draw electric field created by this charge, or if we try to maybe better to draw equipotential lines, then these lines will look like this. So they will be deformed somehow. And because the distance from this plane to each of these charges is the same, then this plane will be equipotential. It will have a potential 0. So, so Green function in this case is, of course, so here it's for z in the upper half plane. So, and of course we can check that when z is real, then these two variables are mutually conjugated to each other. So the absolute value of this ratio is 1. And it is clear that this numerator gives a delta function when we take Laplacian of it, and the denominator just solves a homogeneous Laplace equation because it has a singularity in the lower half plane, and but we are interested in this equation only in the upper half plane. So that's all. So we can check that Laplacian of 1 over 2 pi logarithm of c minus z0 is delta for z in the upper half plane, and so So are there any questions about this? So, hmm? Mhm. Yes, of course. Uh, I don't want to do this because so we will need to take transformation of z, transformation of the zero, and then compare with that formula. So maybe it will not be nice, but uh, hmm? Yes, because grand function is defined uniquely. So what else can it be? Mm, so, hmm? Of course. And boundary conditions are the same. It is zero on this boundary. So, hmm? Because it equals so in principle it equals to minus delta function at uh, uh, at the zero bar, but yes, so into somewhere, and we don't care what happens on there. Mhm. And this one, yes. So, so we can check that Laplacian of this equals to 1 over uh, uh, we can integrate it over some small domain and say that here it's integral of gradient of logarithm, and here it should be some constant. So and the integral of gradient equals to constant because it is one because gradient is 1 over r. So Ah, by the way, uh, mm, mm, probably I didn't tell this yet, uh, but we should tell about existence and uniqueness of solution of this Laplace equation. Uh, yes, because um, Yes, yes, of course. Physically, it will correspond to a homogeneous electric field which goes to infinity, perpendicular to this plane. Which, we don't want. Mm. Mm. Yes, so. Mm. So, do you want to add another way? Ah. Mm. Uh, so where do you want to place it? Somewhere. But uh, oh, maybe I don't understand. So there is this plane on the real line, right? Or so there is this charge. So what else do you want to add? Mm-hmm. But it will change potential in the upper half plane also. So this gain function will know about these charges. So so it will not solve this equation. Why do you want two such planes? Because, it's homogeneous charges or not. Then they will cancel each other because well, if the density of these charges is the same, they will just cancel each other. But if they are different, there will be some constant density of charges which would produce a homogeneous electric field in addition to this field. So it would correspond to addition of something like this u to u plus imaginary part of z. So, yes, of course. So, uh, yes, but we ask for extra boundary condition that well, probably I should write it somewhere that g of z0 goes to 0 when absolute value of z goes to infinity. Yes. Yes. Mm. Yeah. Because if you look at this disk, in principle, infinity on this half plane corresponds to some particular point on the boundary of this disk, and in principle we can have something in that point. So we should also ask for this. Thanks for this question. Actually, I'm going to study a problem in which the asymptotics of this potential is linear at infinity. Because, for example, it makes sense to consider not an internal part, but external part of this unit disk placed in the homogeneous electric field. So we can ask what happens around this disk if we know that at infinity we have electric field with constant asymptotics. And also we can ask those problems, the same problems about incompressible flows. In that case, it is also natural to consider a speed which goes to constant at infinity. Yeah. So let's let's go back. So we know that first consider the uniqueness. So we know that there is this equation with some right-hand side, and for x in some domain D. And we have some boundary condition. Either u of x equals to u0 of x, or so it's directly a boundary condition. We can also impose Neumann boundary conditions. So suppose that we have two such solutions. So then let us call it V, which is U1 minus U2. This solves the same system, but with zero right-hand sides. And so we know that this Laplace equation follows from the variation problem. For the following action. Since this action is always positive, then and then if we find uh, if you find uh, 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 mm, so uh, then we can say that like so if s few is greater than 0, then it is the same as a uh, s of 0, which is equal to 0. And this zero solution is just a minimum of this action by construction. So uh, oh, probably. Um, Uh, it is possible, yes. Uh, if we have this boundary condition, then if it is allowed by boundary condition, then we can also have u equals to for this Neumann boundary conditions. We can have uh, v equals to constant. So it is either unique or unique up to constant, depending on the boundary conditions, on the type of boundary conditions. And concerning the existence, it can also be analyzed based on this mm, on this mm, action. We can just say that mm, we can just say that since this functional is bounded from below by 0, and then we can always find a minimum with some boundary conditions. And if you want some a practical way to do this, we can, for example, solve the heat equation with mm, we can solve the heat equation with some arbitrary initial conditions and take its limit to t to infinity, so that u becomes constant. Mm. Probably I had to tell a little bit more. I had to tell that this functional is not only positively defined, but it is also convex up to this constant, which can appear for Neumann boundary conditions. It is just because it is some some positive defined quadratic form. So it's quadratic in U, and and it is positive for any U except constant. So and it was convexity. We know that the minimum is unique. So are there any questions about this? Mm. Mm. And of course, it was not the case for the wave equation, because we had pluses and minuses in the action. Mm. Mm. So let us consider, for example, the following problem. So mm, let us now consider the external part of this unit disk. And so physically it means that we consider some metal circle or metal cylinder, if we live in 3 dimensions, and place it in the homogeneous electric field E. So it means that U at as it goes to infinity it behaves like minus E imaginary part of Z. Uh, Actually, and let us say that the radius of this disk is R. So it's one boundary condition, and another boundary condition is that U at plus O of 1 over Z 1 over Z. Don't want any constant. And U is 0 when absolute value of Z equals to R. So so the first question is what are the possible basis of solutions of Laplace equation which satisfy this condition at infinity. So what are these functions which satisfy this? So yes. Uh, so so we know that at infinity we have this leading asymptotics. So it is what it is um, I e over 2 z minus z bar. Plus, what can we write in principle? So which functions behave like 1 over z, or which functions decay at infinity and solve Laplace equation? So remember, Laplace equation was dd bar u equals to 0. So hmm? So we know that. If we consider, for example, the bar u, if we look at this equation in this way, we see that the bar u is anti-holomorphic function, and if this anti-holomorphic function behaves like 1 over z at infinity, or even 1 over z squared, then how can, hmm? Hmm? Uh, no, it is homomorphic outside this circle of radius r. So, hmm? Yes. So it is possible to consider such problems, not only in the compact domains. Mm. So, hmm? But if you have some function outside some circle, is it true that it has a Laurent series which does not contain positive powers of z? So I want to say that it is sum of some ans over zn from n equals to 1 from to infinity, plus some bns over z bar n from n equals to 1 to infinity. So is it obvious? Because a function which is homomorphic outside some circle and goes to infinity definitely has Laurent expansions in this domain. So in general, functions have Laurent expansion in some annulus between internal and external R. So. Um, So in general, we can have some uh, internal radius of convergence and external radius of convergence. And singularities are and this function is holomorphic. Uh, in this annulus, uh, so it can be represented as Laurent series from and radius of convergence, external and internal radii of convergence are defined by a position of the first singularity here and there. So, but if it does not have singularities in this in this part of the complex plane, then it is given just by a series which is convergent up to infinity, and also we ask positive part of the series to be zero, because mm, mm, or if you look at this full function, we ask it to be this one. Uh, so mm, we have such an expansion, and uh, now the question. Uh, what should be this coefficients n and bn so that we satisfy this second boundary condition? Like if you substitute that we live on this circle of radius r, then z equals to r e to I phi. So u of phi now becomes like u of z becomes mm, it's not enough space, but it's clear what is written here, I think. So so what should be the solution of this equation? If you ask this to be zero, who should be this ANs and BNs? let me write it maybe. Hmm? So, hmm? Uh, but how? But how can they be zero? How can this sum be zero if it depends on phi? Hmm? Of course. But what does it mean? Uh, ah, but what does it mean for these coefficients? So we have this. So uh, which? Oh, so you mean uh, uh, yes. Mm-hmm. And B1. Mm-hmm. Thanks. So IN greater than 1 equals 0, and the same for Bn greater than 1. So U of R, so U of Z is, and mm, like I E R over 2 uh, uh, plus B1 over R equals to 0. I E R over 2 minus A1 over R equals to 0. So uh, yes, of course, because these functions form bases on a circle, and if you want it to be 0, then each of these functions should be 0. So, so it equals to what? Uh, something like this, and what can we say about this? So it is something like IE, so it minus E imaginary part of Z, and this one is ER squared E imaginary part of Z over absolute value of Z squared. Like, I don't know if it is important or not to write in this way, but now about the meaning of this potential. It is a so-called dipole potential. So we know that if we take just a single a single unit charge, or maybe let us take a charge Q. Then a corresponding potential will equal to well, at some point A, for example. Corresponding potential will equal to 1 over 2 pi q over 2 pi logarithm of z minus a. But if we now consider two such charges, and let us take them opposite. Q at position A and minus Q at position minus A, for example, then this potential will equal to this one. Z plus A. So and now let us try to send A to 0 and Q to infinity. Let us, well, maybe we'll do this later, but we can first write this expression like Q over 2 pi logarithm of absolute value of 1 minus A over Z, 1 plus A over Z. So if we now send A to 0, well, a moment. So I place them this way, so it should be not A and minus A, it should be IA and minus IA. Sorry, minus IA plus IA, because they are shifted in the imaginary direction. So if you now send I to 0, it will equal to so when I goes to 0, it will equal to Q over 2 pi logarithm of 1 minus A over Z times 1 minus plus IA over Z bar. So it is Q over 2 pi QA over 2 pi I over z bar minus I over z. So it is we see that there is some product q times a, charge times distance, and up to some factor we can call this dipole momentum. Hmm? No, I'm saying that we obtained precisely the same expression. So, uh, so we can denote it by d. Uh, so and it will be something like I d over 2 pi 1 over z bar minus z minus 1 over z. So I'm saying that the answer uh, for this potential for this disk in the homogeneous electric field is this homogeneous electric field plus some potential of this kind. And interpretation of this potential can be the following. So it is the same as potential of two charges q1 minus q placed at distance 2a in the limit when this distance goes to 0. So. Because I'm just taking the limit a goes to 0. So everything can be computed up to the first order in a. So absolute value of this is the same as hmm, as hmm, so I can say that 1 over 1 plus IA over Z is the same as 1 minus IA over Z up to the first order in A. So I can add intermediate step. So it is 2 q over 2 pi. Logarithm of 1 minus I over Z. Yeah, absolute value of this. So or maybe I can remove this 2 here and add it with absolute value squared. And then just write absolute value squared as a product of complex number times its conjugate. Hmm? Mm-hmm.
One could see that approximation as a rationalization of the denominator, and then on the denominator we have something that depends from a squared, so it goes to 0 faster than.
Yes, of course. So, uh, oh, and so we see that if we try to iterate this procedure and place, for example, 4 charges or 2 dipole momentums with opposite directions and place them infinitely close, then we can get some higher powers of z. And because of this, such expansions in inverse powers of z are sometimes called multiple expansions. And that, and but from the point of view of this complex analysis, they are just Laurent expansions of some function at in infinity. So, so is it fine? So this was such a electrostatic problem. So probably I didn't write that electric field is minus gradient of phi. But uh, but probably you can remember that this Laplace equation appears not only in the electrostatics but also in hydrodynamics. So, namely, if you want to consider incompressible laminar flow, then we have the speed of flow equal to gradient of phi. So, oh, sorry, I wrote phi, but it was u. So we can have so we have this formula because rotor of u is 0. So it is a gradient of some potential of this flow. And but since it is incompressible, we also have divergence of u is 0 because it is incompressible. And so and so Laplacian of phi is 0. So and this is also described by Laplace equation. And if we have not 0 but something else here, it would mean that we have some sources of fluid at some points. But we can consider problems without sources, like when this flow starts at somewhere at infinity. And you see that in principle, this problem was of this kind. So in this way, we found the answer for this. Well, let me think. No, it's not that problem, because if you want to solve such problem, well, let us solve it again. So here the boundary condition was u equals to 0. Maybe let me replace this u by phi everywhere, because otherwise we can mix. Oh no, we have phi already. Uh, which denotes angle. Let us maybe denote the speed by v and this potential by u. Sorry. Uh, so if you want to consider some boundary conditions, then I should say that not this potential is 0, but a normal component of speed should be 0. Right. So in this case, we'll have this Neumann boundary conditions. And let us try to consider the same problem. So, and now we have v goes to constant at infinity. So you should behave like I z bar minus z over 2v and again plus sum of an over zn from 1 to infinity plus sum of bn over zn zn bar. But now there should be different boundary conditions at so if you have something like this, then it behaves like an imaginary part of z times v. So a field of velocities is a constant at a infinity. But if you want to satisfy this boundary condition at radius r, then we should say that so this derivative in the radial direction is z d over dz. So and then u is the same as is equivalent to uh, dr u equals to 0 is equivalent to something like this. Mm. Mm. So Uh, now we can, of course, say that all coefficients except the first ones are non-trivial, are 0, and for the first coefficients we get what? We get that I over 2. So let us act with this operator here. It will be z bar minus z as before. Here there will be different sign. A1 over z minus b1 over z bar. And it should equal to 0 when absolute value of z equals to r. So now we should combine this term and this one. Uh, so IV. So and uh, so there's this formula, and uh, uh, if it is interesting for somebody, we can draw this field of velocities around this disk. There should be some picture of this kind. I don't remember precisely how it looks like, but something like this. So we can draw it in Mathematica or in some other program. Oh. Oh. So something like this. Oh, this velocity is tangent to the surface of our disk. Is it right? Hmm? This component of velocity, normal component, should vanish on the boundary because this liquid cannot go through the boundary. So uh, it can have only a tangent component of velocity. Mm. So there was such an example. Probably I'll show other examples the next time. So are there any questions about this? So, mm, so if we compare this example with that one, we will see that they're a kind of dual, because here electric field is orthogonal to the surface of this disk, but here it is here this velocity is tangent. Mm. So So today I wanted to tell just one simple thing, uh, mm, and leave other examples for the next time. Uh, so I remember that there are at least three kind functions. One is for the problem with zero boundary conditions and something on the right hand side. So we have this. So uh, mm, so if we have a problem with uh, like a Poisson of u equals to uh, f and x and d, and u equals to u0 on the boundary. And so in this case, a solution for u is given by, uh, or maybe uh, or maybe d and u equals to u1 alternatively. So in this case, we have a formula like u equals to integral over d g of x0 u of x f of x dv plus integral boundary g 1 or g0 g1 of x 0 1 or 0 1 or 0 1 or 0 of x0, maybe x prime, better to say. So I want to say that this gain function for boundary conditions can actually be expressed in terms of gain function for the right hand side. And to do this, we should notice the following thing. So suppose that there are two functions u and v. Better. Not doing better. So I suppose that we have this gain function with zero boundary conditions, and we want to consider the following expression. So so let us consider the following object. From one side, this object equals to u Laplacian of g minus g Laplacian of u. Because intermediate part, which contains product of two gradients, just vanishes. And so it's from one side. And from the other side, we can try to integrate this expression over our domain D. So we can get the following formula, that integral of u gradient of g. So So it's on one side it equals to this one, and on the other side it is integral of u Laplacian of g minus g Laplacian of u over dv. This integral can be reduced to the integral over the boundary. So it is integral d u gradient of g minus d gradient of u ds. And in this integral, Laplacian of g is a delta function, so it gives u of x0. And this is just so we know that f is that Laplacian of u is f, so minus integral of g of x0 f of no, I substituted, so I didn't write what in this grand function, but I substituted grand function of gx0. No, it's an integral in x. So so this is a u of x, and we are integrating in x. Yes, thank you. Yes, it's true. So here we actually need to use the property of this grand function that it is symmetric. G of x0 is g of x0 and x. Yes, so we see this formula here. Actually, we can derive it from here on this property, but anyway. So we see that now u of x0 equals to so there are again two possible cases when u so one option is when grand function on the boundary is 0, then so let us say that it is option 0 and it is option 1. So if it is option 0, then grand function on the boundary is 0, and it tells us that u of x0 is the integral of g of x x0 f of x dv. So and only surviving term is this one, plus integral dn of g of x x0 ds times u0 of x ds. So the first possibility. And second possibility is when normal derivative of g is 0. So in this case, we will have formula u of x0 equals to integral of g of x x0. It's different can function with different boundary conditions. Dv minus the integral of g of x0 u1 of x ds. So the consequence of this is the following: that a green function for the Dirichlet problem is the normal derivative of this inhomogeneous green function, and a green function for the normal problem is just the usual green function, but with a minus sign.
Also, an app for the first integral.
Yes, thank you. So, so is it fine? So.
We have that g for its normal derivative is 0 for the green function of the main problem.
Because it is always like this, we want to separate this problem with boundary conditions and inhomogeneous right-hand side into problems with zero boundary condition and some right-hand side, and problem with a zero right-hand side and some boundary condition. So. This is just so if you want to solve a problem with boundary conditions, then corresponding boundary conditions for the green function should be 0. Okay, so thank you for your attention. See you the next time.